We're going to look at taking the derivative of logarithmic functions. So we need to remember some rules for logs in order to prove the derivatives of these log functions. And so first of all, just kind of recall, if we had some function y equals the natural log of x, ln x, that's an L, not a 1. If we had a function y equals the natural log of x, recall this is the same thing as saying y is equal to log base e of x. Okay, so natural log is just log base e. Let's just look at what it means to be a log. Log y equals log base b of x. There's a couple stipulations. Our base always has to be a positive number. It can't be negative. Our base could not be 1. And what we're taking the log of, that x has to be greater than 0. Can't take a log of a negative number. So if those stipulations held, then logarithms, all they are exponential equations. They're the inverse functions of our exponential equations. To rewrite this, we take our base. Logs are just what is that exponent that we can take that base to get back this value of x. There's another thing that will be helpful for us to remember with logs are rules of logs. And so these right here are going to help us a lot. Where we might have some ugly function that we need to take the derivative of, and we're going to have to apply the quotient rule, the chain rule, and the product rule, and all these different rules within this function. Well, if we can use logs and we can break it down into simpler functions, it's going to make our life so much easier. And so we need these rules of logs in order to do that. And so recall, if you had, let's say, log base b, and we were multiplying two things together, so let's say capital A times capital B, we could rewrite that. If it was multiplication in between here, we could rewrite this as a sum of two logs, log base b of the first A plus log base b of capital B. If we had division, so if we had log base b and we were dividing two things, so A divided by B, we can break this down as a difference of logs. Log base b of the numerator, capital A, minus log base b of the denominator. The other property that's going to help us is if you have some coefficient in front of your log, or if you have some log raised to some power, so log base b, let's say, of x raised to the nth power. This is the same thing as pulling our exponent down front, n times log base b of x. Okay, so those are going to be rules of logs that we're going to need to remember and come back to. And these are also, some of these are going to be helpful for us when we prove how to get to the derivative of the natural log of x. There's one other thing that I have to tell you, and we haven't gone over this, but I'm just going to give it to you, and we're just going to assume that this is true without proving it right now. And so that is your exponential function. So recall e is just a number, just kind of like pi is, 3.14, but it's irrational. It goes on forever and it doesn't repeat itself. E is the same sort of number, and it's 2.718, and it starts going on decimal form and it never repeats itself. E can actually be expressed as a limit. E is the same thing, and you could test it out. We can go in if we wanted to and do it numerically and show it, but we're going to just say that E is the same thing as the limit as h approaches 0 of, actually let's put that as n approaches 0, of n plus 1. And this n plus 1, that quantity is raised to the 1 over n power. Okay, so I'm ready to start with a proof of finding the derivative of the natural log of x. So let's say that f of x is equal to the natural log of x. And we want to find the derivative. Well, we don't know that rule right now, but we do know we can find derivatives by using the limit. So this is the same thing. Our derivative of f prime of x is equal to the limit as h approaches 0 of f of x plus h. So that would be natural log of x plus h minus the natural log of x. So ln of x. And this is all placed over h. So let's clean this up a little bit using rules of exponents and rules of multiplication. We can rewrite this. Well, remember, if we have, going backwards, a difference in between our two logs, we can rewrite this as a log of the first piece divided by whatever you're taking the log of the second piece. So I'm going to rewrite that piece right there as the natural log. My numerator is going to be the x plus h, and my denominator is going to be just x. So using rules of logs, I did that, all divided by h. Well, if we want to, let's get that h, let's rewrite that so that h is not there. So it's not like kind of funky looking. Let's rewrite this. This is the same thing as 1 over h times this natural log of this x plus h all over x. You don't believe me, another way you can think of it is division. So put this over 1 divided by this over 1, and it's invert multiplication. Well, again, let's use our rules of logs. I know that if I have a coefficient out front or a number out front of a log, I can bring this up and move it to the exponent. And so I could rewrite this. This is the same thing as a limit as h goes to 0 of the natural log of x plus h all over x. And maybe at the same time, I'm going to rewrite this x plus h all over x as two separate fractions. So x over x plus h over x. All raised to the 1 over h power. Let's clean that up a little bit. So we have the limit as the h goes to 0. Well, this is the natural log. X over x is just 1 plus h over x, all raised to the 1 over h. So notice that's almost identical. I want to try to manipulate this inside the natural log to look like this. Okay, so maybe we can let n equals this h over x. Then I would have that n plus 1 or 1 plus n value there. So let n equal h over x. So if I do that, I'm going to have, and I'm not going to write anything with h in there right now. So I have the limit as the natural log of 1 plus, well, h over x, we just chose to be n. And let's close this. But I want, let's rewrite h in terms of n. So if I solve for h there, I would multiply both sides by x, right? And so if I do that, I would get that h is equal to n times x. So this 1 over h, I can rewrite this h value is n over x. So when I write that exponent, I'm going to have 1 over n divided by x. The only other piece that has an h in here has to do with this limit. Well, if h goes to 0, what's going to happen to n? Well, remember n is equal to h over x. As h goes to 0, so if I looked at the limit of this, h goes to 0 of h over x, notice that this is equal to also 0. So as h goes to 0, n also goes to 0. So in here, I can say that n is approaching 0. Okay, so I'm almost there. We've almost manipulated this to look like this e function. The only thing is it's 1 over n times x instead of just 1 over n. This is where we're going to go back again, and we're going to use some rules of logs to rewrite that. So notice that 1 over n times x in the denominator, this is the same thing, right, as 1 over n times 1 over x. And recall rules of exponents. If we had some base m raised to a power of n, that was multiplication. So let's bring out that 1 over x and let's bring it up to the power. So I have the limit as n goes to 0 of the natural log of 1 plus n. And this is raised to the 1 over n. And that is raised to the 1 over x. But rules of exponents with logs, we can bring that down front. And so we want to bring this down front, but keep the 1 over n in the numerator. So we have 1 over x, the natural log of 1 plus n, and that's raised to the 1 over n power. And we have a limit as n goes to infinity. Okay, rules of limits. If we have a continuous function, actually 1 over x does not have n in it. So we can technically bring that 1 over x in front of the limit. And then the other thing I was going to say, rules of limits. If we have some composition of functions, which we do, and the natural log of this natural log is the outer function, this 1 plus n raised to the 1 over n is our inner function. If we have a composition of functions and we're taking the limit and that outer function is continuous, Then we can break it down where we take the limit of the inner piece. So we have 1 over x, limit as n goes to infinity. I'm sorry, not infinity, 0. Natural log, what was I just saying? Oh, right. Actually, I want to pull the limit inside. So we actually have the natural log ln of the limit as n goes to 0 of 1 plus n raised to the 1 over n power. I just told you at the beginning of class, this is the same thing as e. So let's rewrite that with e. And so this is equal to 1 over x, the natural log of e. That's probably one other thing I should have reviewed. So this is basically saying natural log of e, log base e of e. So e, what do we raise e to get back e? Well, we raise e to the first power to get back e. So the natural log of e is just 1. So this is 1 over x times 1, which is 1 over x. So if you have the derivative, we just derived it. If f of x is equal to the natural log of x, then the derivative of f of x is equal to 1 over x. So we'll derive it if the base of our log is other than e in a second. I just want to put one stipulation on our rule. Remember, we can't take logs of negative numbers, so we're assuming here that x is greater than 0. Okay, so let's look at finding the derivative of log base b of x. Before we do that, recall, there was a change of base formula for logs. Which says if you have log base b of x, this is the same thing as, well, we want to change this to the natural log. Sometimes you would change it to log base 10, but we already know what the derivative of the natural log is. So let's change this. This is equal to the natural log of what's on top, x, divided by the natural log of what's in our base of b. So we're going to use that fact in order to find the derivative of this. So let f of x equals log base b of x, and we want to find the derivative of this, find f prime of x. So we're not going to use the rules of limits or the formal definition in this case. We're going to use the fact that we know what the derivative of the natural log is now. And so let's first rewrite this. F of x can be rewritten as the natural log of the top x all over the natural log of the base b. And now if we take this derivative, but notice natural log of b, that's just some number. It's what exponent I would raise e to get b. I don't know what b is, but that's just a number. That's a coefficient. It's just an ugly one. It looks ugly, but it's just a number. So we can rewrite this as 1 over the natural log of b times the natural log of x. And so when we take the derivative of this, we know it's just the coefficient times the derivative of the natural log. And we just found the derivative of the natural log was 1 over x. So the derivative is going to be 1 over x times the natural log of b. So now we have the rule that we can take the derivative of any natural log. So if we have y equals log base b of x, again, a couple stipulations, b is greater than 0, b is not equal to 1, x is greater than 0. Then the derivative of that, dy dx, is equal to 1 over the natural log of whatever our base of our log is, so b, times x. I'm going to put the x in front. So 1 over x times the natural log of b. Okay, so now we can start taking derivatives when we have logs or natural logs in the function by using these rules. And of course, it's not going to be so simple. We're going to have multiple rules that we're going to have to apply looking at these examples. Okay, so I said that it wasn't going to be just so simple when we are taking derivatives of logs. So let's say we have y equals the natural log of some function g of x. And that g of x could just be x, or it could be something else. But that tells us, if we're looking at this, we need to use the chain rule, and you need to identify the outer function. So we could let y equal the natural log of u. We want to write it this way. And we can let u equal the inner function g of x. We know that the derivative of y with respect to x, dy dx, that's the one way to show it, is equal to the derivative of y with respect to u times the derivative of u with respect to x. So this is equal to, well, the derivative of y with respect to u. We just said that dy du, derivative of derivative of natural log of x is 1 over x. So the derivative of the natural log of u is 1 over u. So that's 1 over u. And another way to write the derivative du dx of g of x is just g prime of x. So du dx, we have 1 over u times the derivative of the inner piece, g prime x. But we want this in terms of all x, and we know that u was g of x. So this is equal to 1 over g of x, the inner function, times the derivative of the inner function, g prime of x. We can leave it like that, or we can multiply 1 times g prime of x. So this is equal to the derivative of the inner over the inner piece of our log. So same sort of idea. If we're looking at log other than base b. So if y equals log base b, and I'm not going to derive it, it's the same idea, of some function g of x, then the derivative dy dx, this is equal to the derivative of the outer. So that was 1 over natural log of b of the inner, so times g of x, times the outer, derivative of the inner, g prime of x. Okay, now we can look at an example. So if we have y is equal to the natural log of 3x, and then outside of that natural log, we have plus x. And all it wants us to do is find the derivative with respect to x. So I'm thinking of my inner function to be 3x. So the derivative of this first piece, let's just do that. So this is the derivative d dx of the first piece, which is the natural log of 3x, plus the derivative of the second piece, d dx of x. So our outer function is 1 over our inner function, which is 3x, times the derivative d dx of the inner, which is 3x, plus the derivative of x, which is 1. So this is 1 over 3x. Well, the derivative of 3x is just 3 plus 1. Notice our 3's cancel. So we get 1 over x plus 1. Okay. So using rules of exponents can be really, really helpful. So look at this example next. So rules of logs are helpful. So if we had y is equal to t times the natural log of the square root of t. So right now I notice I have to use the product rule, and within the product rule, when I take the natural log of the square root of t, I'm also going to need to use that chain rule. But we can rewrite the square root of t. We've talked about rewriting radicals in exponential form. So this is really t times the natural log of t. Well, the square root of t is the same thing as t to the 1/2. Well, let's use rules of logs. It would make it so much easier if we use rules of logs and we bring that 1/2 down front. So we can say, well, this is the same thing as y equals t times 1/2. I usually put the 1/2 in front. Natural log of t. So now when we go through and take the derivative, dy dt, we need to take the derivative of the first piece, and let's call that 1/2 t. So we need to take the derivative of d dt of the first piece, 1/2 t, times the second, which is the natural log of t, plus the first, which is just 1/2 t, times the derivative of the second. So derivative d dt of the natural log of t. So looking at this, derivative of 1/2 t is just 1/2 times natural log of t, plus, this is 1/2 t or t over 2, times the derivative of this natural log of t. Well, that's just 1 over what you're taking the natural log of, which is t. So I noticed that this simplifies a little bit, that second grouping. I have a t in the numerator, t in the denominator, so those can cancel. So I'm really left with 1/2 natural log of t plus 1/2. So again, using those rules of logs right here was helpful. I think it saved us some time. That we didn't have to use that chain rule when we took the derivative of the natural log. I really want to go into the hard, let's see. I want to show you logarithmic differentiation. And I think when I do that, I'm gonna do it on a new video.